In the previous lecture, we studied how to derive the feedback theorem. So in this section, we are going to learn how can we utilize the feedback theorem in the practical switched mode power supply circuit to derive the system transfer function. So here is the example, right? We use the canonical circuit model of the pulse width modulated converters. So first, we plot the canonical circuit model. So in canonical circuit model, we have the input small signal as Vg. And there is a current source in parallel with it. The coefficient as Js, and the duty cycle small signal ds. And here's another small signal voltage source, which is also contributed by the controlling signal d. Right? So the coefficient is denoted as Es. Then we would have a virtual AC transformer. We use this wave line to denote that this is AC transformer. Turns ratio is 1 to m. On the right-hand side of this AC transformer, we have a low-pass filter network. Here is the effective filter, LE. Here is the filtering cap, C. And here is the output voltage. And this is the load resistor, R. To emulate the load variation, we introduced a current source parallel with the load. As I load. Small signal. So we mark this as the ground on the second side of the transformer. Then we can, so this is the small signal model for the power stage. Then we can introduce the signal processing stage for the negative feedback. So if we assume that we are using analog controller, right, we need to sense the output voltage using a voltage divider network. So here is the R1, R2, R3, and there is a C2 here. So basically, this is a voltage divider. R4. Then the divided voltage is here, right? Is fed to a error amplifier. So another input here is the reference signal. Vref. The difference between error reference signal and the sensed output signal is fed into the error amplifier. And meanwhile, we usually need to introduce the compensation network. For analog control, we introduce a PI compensator from the output and the input. So we denote this as R3, C3. And then the error signal, compensated error signal, is fed to the pulse width modulation block. And this goes to the duty cycle small signal. So in between pulse width modulation and the error amplifier, we can insert the injection, right? So for this power electronic converter example, we inject a voltage source. As small signal Vz. Here is ground. On the left-hand side of Vz, this is the Vx signal. And on the right-hand side of the injection point, we denote as Vy. To simplify the analysis, we mark several impedances. So basically, we denote this network R1 series with R2 parallel with C2 as impedance of Z1. R4 we denote as impedance of Z2. R3 in series with C3 we mark as impedance of Z3. Okay, so now let's look at the overall diagram, right? We can see that the output signal is the Vout, Vs. And there are three inputs of the system. One input is the reference input. And second input is the line input. And thirdly is the load input, right? So if we do not consider the injection of the external source here, there are three inputs. Based on the previous knowledge, we learned that the output can be expressed in the combination of the three parts. First part is contributed by the reference input. So we denote the coefficient as GR. Second part is contributed by the line input. The coefficient is denoted as GGS. Third part is contributed by the load, right? So as we previously denoted, the load is controlled by the output impedance, so Z out. Okay, next we can try to apply the feedback theorem we learned to better solve this transfer function. So based on the feedback theorem, all those three transfer functions can be decoded into two parts as we previously derived. For example, G reference can be decomposed into two parts, G infinity R, T over 1 plus T, plus G0 R, 1 over 1 plus T. Similarly, for GG, line to output the transfer function, we also can decompose it into two parts, G infinity zero. Last one is the Z out. Z infinity out t over 1 plus t. Z0 out 1 plus t. So next step is we can try to solve the infinity coefficient and the zero coefficients. Then we can find out the overall transfer function for those three parts, right? So let's do them one by one. So first step, we can determine the infinity part, right? So determination of G infinity. Remember, when we analyze G infinity, we will consider that the Vy is not to 0. So then we look at them one by one. First is the G infinity R. So G infinity R equals to, in S domain, right? Equals to, based on the definition, the ratio between output and reference. Given the condition that, so here we care about the impact of reference. Then we consider the line input and load input are both 0. And meanwhile, we know Vy to be 0. So those three conditions will significantly simplify the analysis. So basically, if Vy is not to 0, right, then we would have the, so denote the signal here is V minus, right? Then V minus can be treated based on the voltage divider principle, right? V minus will be equal to, here is output voltage divider. So V times the voltage divider network. So the impedance of here, looking downside, right? If you look down, because Vy is not to 0, it's like we kind of put this into ground. Then you will see that these three will be indeed in parallel with Z2. So this voltage divider is easy to solve, right? The denominator is the parallel of Z2 and Z3. And the denominator is Z1 in series with parallel of Z2 and Z3. So easy to solve if Vy is not to 0. So based on this formula, right? So this is the expression for V minus. And the error amplifier will enforce that the positive input and negative input, they are matched. So V minus should be equal to V reference. So it's easy to calculate the ratio between output signal and the reference, right? So we can derive that the G infinity R equals to V divided by Vref. So the left part will be exactly the circled part. G infinity R will be the ratio between output signal divided by reference signal. So it will be equal to the this fraction, 1 over this fraction, right? So Z1 plus Z2 parallel with Z3 divided by Z2 parallel with Z3. And now if we look at this G infinity R, so we can extract some interesting information. So basically, if we consider DC operation at DC, meaning that S equals to J omega equals to 0, right? Then we would have G infinity R 0. If we look at those impedances at DC, the capacitor will be open circuit in DC. So it's kind of this part is gone, right? And this part will be equals to R2. So we only have the resistor parts in this branch, so that the impedance formula can be significantly simplified as a resistive voltage divider network. So the numerator is the sum of the 3 resistors, R1 plus R2 plus R4. Denominator is just R4, because here is in DC is open circuit, opened. So what does this mean, right? This means that the DC ideal output voltage can be solved, right? Can be solved by this resistive voltage divider network. By properly designing the values of those resistors, we can properly design the target DC voltage. So next, let's look at the G infinity, G. So similarly, right, this can also be expressed as G infinity, G S, based on its definition, will be the ratio between output signal and the line input signal under the similar group of conditions, right? So V reference equals to 0. I load is 0. And Vy is not to 0. So for this set of conditions, we can learn that the V reference will be 0. And meanwhile, Vy is not to 0. Right? Those are given conditions. So because of those two given conditions, that we can easily derive that V minus equals to V reference equals to 0. So if V minus is 0, then the output signal is also 0. So if output voltage is 0, then this fraction will also be equal to 0. So we can derive that the G infinity G will be equal to 0. So what information does this argument tell us? So it tells us that with infinite loop gain, the Vg the line input small signal does not influence the output signal. Thirdly, we care about the Z, the output impedance part, Z infinity 0. Again, we list its definition. Z infinity 0 equals to the output voltage minus divided by the load change, I load, given the set of conditions that the other small signal inputs are 0 and Vy is not to 0. V reference equals to 0. Line input is 0. Vy is not to 0. So this derivation is pretty similar to derivation of G infinity G. So similarly, we can also obtain that the V minus equals to 0. And the V out equals to 0. So that Z infinity 0 equals to 0. This contains similar meaning as I wrote here. Means that with infinite loop gain, very, very large loop gain, the I load does not influence V out. That's the conclusion we made here. Okay, now let's erase the blackboard. Okay, in the previous page, we have derived the infinity part of those transfer function. And now let's continue to move on to derive the 0 part. So determination of G0. So in order to derive G0, we need to know the Vx to be 0. So Vx should be null to 0. So we can analyze them one by one. So first, let's analyze G0R. G0R in S domain equals to the output signal divided by reference signal. Given the condition that the other small signal inputs are 0. And also the Vx is not to 0. So if we look at here, right, if Vx is not to 0, the ds will be proportional to Vx. So d small signal equals to 0. So this means that the output voltage can be found out from the V minus, right? So look at the primary side of the transformer. D is 0, so here is 0, open, short. Vg is 0, so here is short. So it's like the primary side of transformer is shorted. So we can equivalent to that, the secondary side of transformer is also shorted. Then the output voltage can be founded from V minus in these parts to ground, right? So here is like shorted. So if we look from here to the left, this will give us an equivalent impedance of Z out. So Z out will be the parallel of R, C, and LE, because the secondary side of transformer is shorted. Then the output will be the voltage on the output impedance, right? So Z out in series with Z1. So this is a impedance voltage divider network equals to V minus times the voltage division ratio of this impedance network. So the numerator is Z out. Denominator is the sum of Z1 and Z out. So based on the definition of G0R, we can solve the ratio between V out over V minus. And also we know that V minus should be equal to the reference. So that we can derive GOR will be equal to this fraction. That's the expression for G0R. So this tells us that the direct forward transmission gain is non-zero. All right. Secondly, let's try to derive G0G for G0G. Again, we list the definition for this parameter will be equals to output signal divided by the input, line input signal, given the condition that the other small signal inputs are 0. And Vx is not to 0. So let's look at the diagram, right? So if Vx is not to 0, and V reference is 0, right? Then the V minus, the minus input of the error amplifier also equals 0. B ref equals 0. B minus also equal to 0. So that if we look from the line input to the output, so for this time, we no longer have the equivalent short, right? Because VG is non-zero. If we look to the right-hand side, we will see that the voltage gain from VG to the output will contain two parts. One part is M part, right? So the D is 0 because Vx is not to 0. Here is open, here is short. So the transfer function contains the turns ratio of transformer M. And the transfer function of HE is like the transfer function of this low-pass filter network. So L in series with C parallel with R parallel with Z1. Okay, so that we can easily write the expression for GOG will be equal to the product of voltage conversion ratio times the transfer function of the low-pass filter network. So we can see that if we observe this formula, we can see that this coincides with the open loop GVGS. All right, so next, let's look at the output impedance part, G0O. So we can list the definition mathematically. This equals to minus output voltage small signal divided by load change I load, given the condition that the other small signal are 0. And Vx is not to 0. So similar to analysis of GOG, right? G0G. So we can similar. We have the reference small signal to be 0. And due to the ideal op-amp feature, right? So the minus input also 0. Then we look at how the output voltage will be affected by the load current. So you will see that the output voltage will be affected by load current by the impedance looking from here to ground, right? So it contains two parts. The first part is the Z-out part, right? For this condition, Vg is 0. So again, we have the secondary side of transformer shorted. So to the left, it's going to be Z-out. To the right, here is ground, right? So it's like we have Z1 in parallel with Z-out. So that I'm going to write it here. Z-out 0. So Z0 out S will be equal to the ratio between the output voltage divided by load current variation will be equal to Z out parallel with Z1. Okay, so that's till now we have fully solved those 6 pair of coefficients of G infinity R, G0 R, G infinity G, G infinity G0 G, Z infinity 0, and Z0 0. Okay. All right, we have erased the blackboard. Previously, we have derived the infinity part and 0 part of those 3 pair of coefficients. And the last task remaining is we need to figure out what is the loop gain, right? So step 3, determination of loop gain T. So remember when we introduced the definition of T, so we consider that the input voltage source is 0. So line input is 0. So it's like the Vg equals to 0. And based on this condition, we can again write the definition, right? Definition for loop gain. So Ts will equal to the Vy small signal divided by the Vx. So it's like Vx goes through this entire system until it comes back, goes through one loop, right? We can find out loop gain. And given the condition that the other small signal parameters are 0, so Vref 0. Load current variation is 0. And input voltage source, Vg, small signal, is 0. So, for example, if Vref is signal, Vref is 0, then this inverting input is also 0, as I marked here. And if I load is 0, then the current source can be equivalent to an open circuit, right? To an open circuit. So, therefore, we can write that the Vref equals to 0, and the V minus equals 0 due to the ideal op-amp feature, right? So then we can derive that the Vy over V output is like the voltage here divided by the voltage here. So this can be obtained by the very fundamental knowledge we learned in the analog circuits. So this is like a non-inverting or op-amp configuration, right? So the output voltage divided by this input voltage will be equals to the impedance Z3 divided by Z1, right? Because here is ground. So this would be equal to Z3 over Z1. Then we can write the output voltage by the GVD formula, right? Remember, we can express output voltage by the input Vx times 1 over Vm, which is the duty cycle, right? So this is the definition for GVD transfer function. And d cap equals to Vx over Vm. All right, so we can write the expression for GVD, control to output the transfer function, to be the product of the ES, right, times the voltage conversion ratio M times the transfer function of the low-pass filter network. Again, this low-pass filter network, the R is parallel with C and parallel with D1, right? Times HES. Then we can write the expression for TS. Loop gain transfer function will be equal to GVD times 1 over Vm times Z3 over Z1. So that's the expression for the loop gain transfer function. Okay. So till now we have fully solved the 3 parts, right? Infinity part, 0 part, and the loop gain part. So step 4, we can summarize. In summary, we can express those 3 transfer functions separately. GRS include 2 parts, right? As we listed here. Now I'm going to rewrite this set of equations. So for G infinity R, this equals to the Z2 parallel with Z3 divided by Z1 in series with Z2 parallel with Z3 times T over 1 plus T plus GOR 0R, which is Z out over Z1 plus Z out times 1 over 1 plus T. And secondly, for GGS equals to, this is relatively simple. So only one part is non-zero, right? Equals to voltage conversion ratio times transfer function of the low-pass filter divided by 1 plus T. So this is 0, this is non-zero. And thirdly, output, Z out impedance equals to, so this is 0, this is non-zero, right? We have just derived Z out as equals to Z out parallel with Z1. The Z out is RCLE in parallel, right? Divided by 1 plus T. And all those 3 terms, they contain the loop gain, right? So where the loop gain T equals to GVD as 1 over Vm times Z3 over Z1. And GVD equals to ES times M times HES. Okay, so in this lecture, so we're combining the specific circuit example we learned how to utilize the feedback theorem to solve the circuit problems. So by using the feedback theorem, we can generally describe the loop gain and the transfer function of the circuit. So indeed, it's a very useful tool for us to analyze the AC model and dynamics of the closed loop system. So I hope that you can absorb